Okay, everyone, welcome to today's PacTrans hosted webinar. My name is Cole Kopka. I am the Assistant Director of PacTrans. We are the Region 10 University Transportation Center funded by the U.S. Department of Transportation for the Pacific Northwest. We have 7 universities in our consortium, including the University of Washington, Washington State University, University of Idaho, University of Alaska Fairbanks, Boise State University, Gonzaga University, and then the people you'll be hearing from today are from our partners at Oregon State University. And our 2 focuses are mobility and safety as a center. Really glad to have you here today. Before I introduce our presenters, for those of you who might be new to a Zoom webinar, I want to give you a little bit of a rundown on the functionalities you'll find today. If you move your cursor over your screen, you'll see 3 icons at the bottom. The first that I will highlight is the Q&A box. This is where we would ask you to put any questions you have to the presenters throughout their presentations, and especially at the end if there's time for some questions and discussion. That's primarily what they're going to be focused on looking at. There is the raise hand option, and so if you would prefer to audibly make a comment or raise a question, you can hit the raise hand button, and we can call on you and unmute you, and you can ask that question verbally. And then the last is chat, and you have the ability to chat with panelists, but not amongst one another. And so generally, we would ask you to use the chat for any technical issues that you have, and then we'll try to help you troubleshoot those things from behind the scenes. So with that, I am going to introduce our 2 presenters for today. The first is Michael Scott. He is a professor of civil and construction engineering at Oregon State University. He is a developer for the OpenSees finite element software framework. His teaching and research interests are in nonlinear structural analysis and computer methods for engineering applications. And the second presenter will be Minjie Zhu. He is a research associate in the School of Civil and Construction Engineering at Oregon State University as well. He develops modules for OpenSees for fluid structure interactions using the particulate finite element method. In addition to FSI, his research interests include numerical methods and computational mechanics. And so with that, I'm going to unshare my screen and invite Michael to come forward, and he can begin.
Okay, thank you, Cole, and thank you, Cole, for hosting the webinar and giving us an opportunity to talk about modeling tsunami loading on bridges using OpenSees particle finite element method, or PFEM. Okay, so this is work sponsored by a variety of sources, including PacTrans, and I'll talk about some of the other funders of this work in the presentation. Okay, so kind of the overview, we'll go in 2 parts. So I'll do part 1 and talk about a little bit of background on tsunamis, and then tsunami loading equations for bridges. And then in part 2, Minjie will give a drill down into OpenSees with the PFEM and how we used the PFEM to do numerical simulations that led to the loading equations, and then also go through an example of using OpenSees PFEM analyses. And then we'll have time for questions. So a little bit of background. Tsunamis is a literal translation from the Japanese word for harbor wave, and these can be caused by earthquakes, landslides, and other phenomenon. Several recent tsunami events have stressed the importance of the potential impact and observed impact of tsunamis on our built environment. All right, so the 2004 Indian Ocean tsunami, 2 recent tsunamis in Chile, as well as the 2011 Great East Japan earthquake and tsunami. This image on the right is from that event. Okay, showing inundation, across urban areas, bridges, buildings, causing a lot of damage. The last major U.S. tsunami was in 1964. This is from the magnitude 9.2 Alaskan earthquake, where waves reached British Columbia, Pacific Northwest, as well as Northern California. Okay, so really, these recent tsunami events have really, again, kind of brought tsunamis into the forefront. So in terms of the Pacific Northwest, we're faced with the threat of the Cascadia subduction zone, which is less than 100 miles off the coastline, and it's caused by subduction of this Juan de Fuca plate under the Cascadia zone, but there's potential for long duration earthquakes, 3 to 5 minutes of ground shaking, followed 20 to 40 minutes later by a tsunami, which could be up to 30 feet high and over half a mile of inundation on the coast. All right, and then based on written records as well as geologic data, turbidite history, the last major CSZ event was in January of 1700. All right, these are written records from Japan of orphan waves, all right, as well as sampling of turbidites on the Oregon coast. And based on history going back before 1700, there's a about 10% chance of a similar event happening by 2030. All right, so definitely a clear and present danger, as they say. Okay, and this was all brought into the forefront by of all places or of all things, a New Yorker magazine article in 2015 called the next big one, but describing how this could be potentially the worst natural disaster in modern U.S. history if there is a big or when there is another major CSZ event. And basically, quoting the article, everything west of I-5 will be toast. And this is due in large part in Oregon, before 1974, there was no seismic design code. All right, much of the critical infrastructure was built before 1974. All right, of course, the interstate boom was in the 1950s. Lots of buildings built before 1974. So, but again, this article really stressed the potential impact of a CSZ event. Okay, so drilling down into or focusing on bridges, right? Bridges serve as lifelines for evacuation and recovery, during and after an earthquake and tsunami event. So of course, bridges must be functional after ground shaking, but they also need to withstand subsequent tsunami attack. All right, and currently there's no bridge design provisions for tsunamis in the U.S. There's some for hurricane type storm waves, but tsunami waves are quite different, similar but different in many ways. Okay, so to address this knowledge gap, back in 2014, PEER, the Pacific Earthquake Engineering Research Center, developed or held a workshop to look at how well can we simulate tsunami loading on bridges. And this photo is from that workshop, and many of the researchers shown in this photo participated in what followed, which was a pooled fund study involving five western state DOTs with a vested interest in tsunamis around the Pacific. So Oregon, California, Washington, Alaska, and Hawaii. And the objective of that pooled fund study was to develop a design guide specification for tsunami loading on bridges, which is what I'll give a kind of high level overview here in the rest of this part one of our presentation. Okay, so developing the design guidelines or design specs, you have to know what the hazard is, right? So probabilistic hazard analysis done by Pat Lynette, University of Southern California, almost said University of South Carolina. I'm from North Carolina, but slipped out. But Southern California, as well as Honky Theo, one of his collaborators, developed, based on probabilistic analyses of triggering events all around the Pacific, what's kind of the maximum credible flow height and flow speed that we can expect at different locations along the coast of Oregon, California, Washington, Alaska, Hawaii, you know, at different grid locations. And these grids, you know, we kind of modeling open shallow water flow, you know, around the Pacific. All right, so you can't get too refined. So the grid sizes were between 10 and 60 meters. Okay, so this is just kind of showing an overview of the you know, looking at a large scale, you know, what can we expect based on different triggering events. And then this kind of blue and yellow image in the middle is showing different mapped points along the Oregon coast. All right, and then some, you know, transect analysis and other things that can go into finding the maximum credible flow height and flow speed. Okay, so then using that flow height and flow speed, and we assume a tsunami bore profile, such as shown down here, you know, for horizontal velocity of an approaching wave going from left to right, as well as a vertical profile of velocity. And then from that, you know, find for different bridges, what's the total horizontal and vertical forces on the superstructure. All right. So we validated this approach using PWRI experimental data, which Minjie will go into a little bit in the second part. Okay. But, you know, we don't want to model, you know, we don't want to have to model very large domains. All right. So we kind of move the tsunami bore right up to the bridge location. If I can, but you know, if, you know, bridge will be located like right here. Okay. And then we, you know, ram a tsunami bore up against it, and then, you know, see what the impact is in terms of forces. All right, so compare that to experiments. The simulation approach, you matched pretty well. Okay, so and then we took this, you know, approach from, you know, experimental data to extrapolating out to different coastal bridges. All right, so for example, US 101, Siletz Bay Bridge in Oregon. Based on the hazard analysis, we can expect a 10.1 meter flow height and a 5.5 meter per second flow speed for this location. Okay. All right, and then so this is our bore in the lower left, and then the bridge model. It's an open girder bridge, and then you're just looking at the simulated results down here in the lower right. All right, so we, you know, took, you know, what I'll show next is we took a lot of these bridges, or several, you know, real bridges along the Oregon coast, as well as and then look at different flow heights and flow speeds to develop loading equations. So those nominal type loading equations were based on some work done by Azad Bakht and Yim at Oregon State on breaking tsunami loads down into a hydrostatic component as well as a hydrodynamic component. So kind of a height-based term here for a nominal horizontal load, and then a velocity squared based term for the hydrodynamic force. Kind of a schematic or simplification of the loading process is shown down here on a superstructure. Okay. But, you know, these nominal loading equations can give us overly conservative load estimates. All right. So when compared to simulations, which, if we believe the simulations are a reasonably good reflection of the load effects to expect, right? So we need to adjust these loading equations using two reference terms on the hydrostatic and the hydrodynamic load effects. All right. So for instance, you know, if that bridge I showed a couple slides ago, if we compared on the x-axis the horizontal steady state force from the simulation to what the unfactored loading equation would predict with C1 and C2 equals to 1, right? You see that there's, you know, a large, you know, amount of conservatism or overestimate of the loading based on the equation. Right? Again, if we believe that the simulation gives us a good prediction of the forces. So we can adjust these factors C1 and C2 basically through regression, right, to get a better, you know, kind of bring these points down onto this 1-1 line, which is shown in blue there. Okay. All right, and then also, noting that the steady state force is fairly easy to, or relatively easy to determine compared to impact, right? We then used regression again, which I'll show in the next couple slides, to relate the impact or steady state impact force to the impact force. So this kind of peak impact force here, the very transient type loading, to the more steady state constant force after impact. Okay, so again, press the fast forward button. All right. We did these analyses for 6 different bridges along the Oregon coast and varied the flow height and speed around the maximum values given by the tsunami hazard analysis, right? And then came up with all these dots here on the left for different bridges, different flow heights, different speeds, right? And the adjustment factors that we came up with for open girder bridges are shown here, all right? 0.75 and 0.8, 0.75 on the static term, 0.8 on the dynamic term. All right, and then relating steady state force to impact, the factor was about 2.1. Okay, so the impact force was a little over twice the steady state force. Okay, and again, more details on this process are given in PhD dissertation by Zhonglang Ji from 2019 here at Oregon State. Okay, and then for box beam bridges, all right, different type of superstructure, right? We found different coefficients for the static and dynamic terms, and then a different coefficient for the impact term as well. But again, all based on regression analysis, and we're still tweaking these factors a little bit, all right, but there's many other things to consider. Not every bridge is straight or perfectly flat with respect to flow, all right, so there's other factors for bridge geometry that we account for, like skew, slope, and super elevation, as well as factors for small debris, and then just completely separate load cases for large debris, think shipping containers or vehicles striking a bridge, and then also substructure analysis, on the piers, as well as geotechnical considerations for substructure or scour, sorry. Okay, and then also uplift and downward forces. But these draft design specifications are under review by AASHTO T3 and T5 currently. Okay, so given pretty glossy overview on the loading equations, and now I'm going to turn it over to Minjie, who will give some details on how OpenSees is a PF particle finite element method within OpenSees, how we use that to do fluid structure interaction. Okay, so I'm going to stop share and then hand it over to Minjie.
Hello everyone. I'm Minjie. In the second part, I will focus on the numerical simulation of the tsunami loading on bridges, and show how to do it actually in OpenSees. So first, I want to give a very brief introduction to the OpenSees Pi, a Python interpreter of OpenSees. So first, with OpenSees Pi, we actually bring OpenSees to the Python community. So if you're already a Python user, it natively runs with other Python packages, your Python programs. But more importantly, we bring Python to the OpenSees community. Since OpenSees Pi is just another Python package, you can run OpenSees Pi with a lot other Python packages, such as Jupyter Notebook, NumPy, SciPy, Matplotlib, Pandas, TensorFlow. There's a lot. So you can just integrate your OpenSees simulation with other tools to do data analysis, statistically analysis, or even machine learning stuff. So this is just very briefly for the OpenSees Pi. And OpenSees Pi extend OpenSees framework for the tsunami simulation modeling. With a method called particle finite element method, or PFEM. It is a fairly new method created around 2004 by Oniate and Edelson. It's a little bit different to the traditional CFD approaches. It uses Lagrangian framework, which is similar to what we used in solid mechanics, structural mechanics. So it can be easily used to couple the tsunamis with the structural models like bridges. It also aims at solving multi-physics problems and the large deformations of the domain. So, but all these features are very suitable for our problems, tsunami loading and bridges. There's a recent paper for the review of the methods published this year in August by the authors of the PFEM. And at the right, this figure actually is from this paper. It shows a classic dam break problem and comparisons with the experiments. And actually, I will show the same simulation in the OpenSees. But before that, I want to mention another, not feature, but aspect for the PFEM in OpenSees. So in OpenSees, we mostly implement all the features of the PFEM, but we have a new handling of the particles that is different to the traditional PFEM. So traditionally, PFEM assumes particles equals to the finite element nodes. So each node of the fluid is a particle, so it can move freely. But the problem is, if you have a large number of particles, your model just grows dramatically, and it's just overkill the total performance. And you have to do like global dynamic tessellations. You just kill the performance. So in OpenSees, we do create a called background mesh. So we separate the concept of particles and finite element nodes. So now we can have a set of particles, fluid particles, and from that particles, we can create a background cells or background mesh for the fluid. So we only need to do local dynamic tessellation, and there's no boundary detection is needed. In the next slides, it just quickly goes through these methods. So first, yeah, we have a bunch of fluid particles defined. Then we create a background mesh. Then we put our structures on this mesh. We identify where is the locations of the structure. Then we do a local Denali triangulation just around the structure. And lastly, we remove these empty triangles here, the empty triangles around the structure. And the background mesh is finally created. This method we find is very efficient and fast to couple the structures and the particles. And here's the dam break example. So again, on the left is the figure from that paper of the review of the PFEM. And on the right is the our implementation in the OpenSees. As you can compare this to the left, with the background mesh, the domain, the fluid domain is actually more smooth. So we get more smooth results because you can see the left, in the traditional PFEM, we have a lot splashing of water. These water particles just flying out is even more splashy than the experiments. So the background mesh really helps to reduce, the oscillation of the results. And here's another example. This is another water column hit a bridge pier, and we put a gate here. So when the gate moves up, the water comes down. So then this is the animation of the the interaction. You can see the water particles hit the pier. Yep. And now I want to focus on this PWRI experiment and its modeling in OpenSees PI. I will go through a breakdown of the scripts and how we do it and how we get the results and compare with the experimental data. So the experiment setup is like this. You have a water tank, standing water, and the bridge superstructures and wave gauges right before the bridges. And this is another direction look at the model. So the bridge is actually the same length wise of the wavefront. So it basically a 2D problem. So we run it in 2D. And the data collect our pressures on the bridges. So on the top and beneath it and the front, and also the horizontal and vertical reactions recorded from the bridge. The bridge. And this is the dimensions of the bridge. The tool we use is called the Jupyter Notebook. We basically write our code in scripts in the Jupyter Notebook and run it, and then we can post-processing it. So now I'm gonna leave this PowerPoint and open the link of the Jupyter Notebook. So if you take a quick look at the notebook, we have different cells of codes, and we also put the pictures here. It helps us or you when you're developing your model. So now I just go to a very quick rundown of this codes. So give you just an idea how we do this, and you also can do it. So the first is to create a model. So that's the model we wanted to create. Waters are created as particles. Bridge, that's regular OpenSees structure, and these walls are fixed boundaries. If you use OpenSees before, you probably know familiar with this wipe and model. And you also import some packages, of course, OpenSees PI and a few others. Then based on the dimensions, we create variables for the wavefront, variables for the bridge structure. And this part is the parameters or properties for the fluid density, viscosity, and structure properties, density, elastic modulus, Poisson coefficient, and mass. And we want run total 15 seconds, and the simulation is time step is between 0.006 seconds and 10 to the negative 4 seconds. And for this example, we run for the case 1. This experiment has different cases. Different cases has different reservoir and standing water heights. So this is only for case 1. So in this part, we first define a recorder. You probably already know the node recorder and element recorder in OpenSees, but this is a new recorder called background PVD recorder. So it just saves every model information to PVD file, and then we can open it in the peer review. And also OpenSees implement a new method called mesh. So it takes several geometric parameters and mesh the domain, like do the solid mesh, line mesh, and here we do the particle mesh. So I give it the fluid elements I want to use, the shape of the the water in the reservoir, and I mesh it so it will create all the particles as the reservoir. And this will create the particles for the standing water. So now we have the particles created. Then we need to create the structure model. So this is very typical and regular structure model in OpenSees. Create a bunch of the boundary nodes of the structure, the structure material, and mesh line means I mesh all the boundary lines of the bridge. And with the boundaries, I do another mesh. It creates tri-3-1 elements of the structure. And the last step for modeling is to create the walls, the float wall. And also use the mesh line, create the wall nodes, and I fix the nodes. I add mass to the structure. And the final step is to create the background mesh. Remember in the few last slides, we have particles, we have structure model, then the background mesh combine the particles and the structure models all together, then create the fluid and structure interaction model. So with the Jupyter Notebook, I can have the scripts, then I can run it. So here I just go to cell, run all above. So I run all above cells. It takes 3 to 2 minutes to run because I'm running in a virtual machine. So you see the stars here, that means it's running. As it's running, I will just go down, explain this analysis part. So first we set up the analysis like the normal OpenSees analysis. We have constraints, number, tests. So a few analysis options are PFEM specific, like this test, convergence test for PFEM. Usually we do like residual test or unbalanced force test. But here we need test for both velocity and pressures. So we have different tolerance for them. And this this PFEM integrator is actually a Numerical integrator, but it's different because it takes velocity and pressures as the primary unknowns. And this PFEM system is the solver for solving the coupled FSI system. And this analysis is a dynamic analysis, but it takes the maximum and minimum time step we want. And also do a couple other things to make sure the PFEM is running good. Okay, so now this model is created. If we list this directory, we see a couple files are created. So one of the file is called the .pvd file. So now I'm gonna just pause the sharing, stop the sharing here. And I will go to peer review here. So this is peer review. I will open this file I just created and open it. So this is the model we just created. So that's the reservoir. If we look closer, you can see the red dots are the particles and the white dots are the background nodes. So we have the water tank, we have the standing water, and our bridge is here. Meshed with the Tri31 elements. So usually what I do is I create a model and view it in the pair view. Is I'm fine with the model, then I just keep going with the analysis. So let me go back to the notebook. Okay, so now we have set up the analysis. Then the next thing is to get results. So the results we want to look at are pressures at the same locations with the experiments and total reactions. Since we don't know exactly the location they measure the pressures, so we just get a few pressures from the nodes around that location and do an average. So now I just use Python functions, define the Python functions to get the pressures, and another Python functions to get the reactions. Then I create an empty list for the response history of the pressures and reactions. And now I can just start perform the analysis. The analysis is in a while loop. While my current time is not reaching to the total time, I do analysis. So for PFEM, we do one step at a time because we need to update the background mesh, the particles, and move them to the new position. So in every time we do one step and we do a remesh, between them is calculate the reactions and append the pressures and the reactions to my list. And at the end, I save all my data to the files. I can run it here. So I stopped here. So now I just run all below. So it will run everything below. So you can see running starts and it just goes to step by step. Since we need to go to the 15 seconds, it takes a while to run. I think we don't have time to run here. So I will just stop here and show some results I have run. Okay, let me stop it here. And I head back to my presentation. Okay, so this is the Jupyter Notebook. So here's the results. So there's 4 videos here. So this one is from the experiment. They record the interaction, the impact of the water and the bridge. And in this video, I show the whole flume simulation, starting from the water gate is lifted and the water hit the bridge. But since it's in a large scale, so you cannot see it very clearly. So these 2 videos, this one is a closer look at the gate to show you how this wave are populated from the reservoir, and the waves start running to the right. And this video shows just focus on the bridge. So at about the 3rd second, the waves arrives to the bridge and hit bridge, and the water just go on the bridge. So it just corresponds to the experimental video. So this video shows qualitatively comparison of the results. We also want to see quantitatively the comparisons. To post-process the results, we also used Jupyter Notebook. So here I created another notebook just to plot the results. I can also open it. Okay, so this is another notebook to do all the post-processing. So first I load all output data. So just load these reactions and pressures. And the first thing to compare is the wave height and velocities at the wave gauge. I think it's this one, this wave gauge. And we use matplotlib to plot the results and make it larger. So this is the wave velocity at this gauge, and this is the wave height at the location. Comparison between experiment and simulation. And we also want to plot pressures at these 4 locations. To plot here, make it larger. So I can zoom in here. You can see our simulation results are more oscillating than the experiment's results. As I have said, background mesh already gives smoother results than the traditional PFEM, but it's still very oscillating because that's the nature of the problem. You have very highly changing domain, very complicated interaction between the fluid and the structure. So you do get these oscillations. And the experiment data are more smooth because they have the data is filtered with I think it's at the 10 hertz filter. So okay, that's for the pressure. And we also compare the reactions. So this horizontal and vertical reactions comparison. See, the simulation is also more oscillating. And lastly, we do a filtered results with 10 hertz. So now you can see that the results are much better to the experimental data. Okay, in summary, PFEM is a fairly new CFD approach. So it's very suitable for modeling tsunamis with traditional structures in the structure engineering. And the coupling we've done is very strong. We strongly couple the compatibility and the continuity at the interface. And OpenSees PI can run this combined tsunami and structure analysis with all existing structure model. What model you want to use, you create your model, and you can add the particles and add the fluid, and then you can run the analysis. With this tool, we can run many numerical simulations with different configurations, geometries, and materials. Our ongoing efforts include to combine earthquake engineering, ground motions with tsunami noding. And also we want to include debris impact on the bridges. If you want to know more information about OpenSees PI or PFEM, you can go to this website. We created as a documentation for OpenSees PI for how to install it, all the commands you need, and examples. I think I'm gonna just stop here, and I want to see if there are any questions for me and Michael.
Okay, thank you, Minjie. I guess I'll kind of look at the questions, take Cole's take Cole's job a little bit, but I'll read through the questions. But so a question from Farzine. Hello, Farzine. Can we do 3D analysis in PFEM? Answers yes. And then the visualizer, that I guess, was that the ParaView that Minjie was showing? Yeah, ParaView, right? Which is it's available on Windows and Linux,
Mac.
Mac. Yeah,
free software.
Yeah. Okay, and I think Farzine, maybe you came on late, but Minjie showed a couple of 3D simulations from OpenSees, so that'll be in the recording. So then, let's see, Balint. Hello, Balint. It's good to see familiar names here. But how many particles were created for the model? I guess this is for the PWRI model. Minjie, about how many particles were there?
Yeah, the number of particles really depends on. So you can have as many as you want, but typically what we do is we depends on the size, the mesh size of the problem. So since we use background mesh, so the background elements are in each little cells. So each cell, its size is the mesh size you assigned. Then I assign a number of particles in each cell. For example, typically we use like 2 by 2. So each cell have 4. For 2D problem, each cell has 4 particles, then adds up to for the whole domain. So totally it adds up to like thousands or maybe 10,000s. We run up to, for 3D problems, we run up to like maybe 1 million particles. Particles are not problem because we separate particles and finite element mesh. So you can have more particles than the nodes.
I guess for this specific example with the PWRI experiment, like roughly how many particles or how many equations were we solving? I think it was in the output when you were running it, but a couple thousand equations, I think.
Right.
Yeah. And then another question from Balint, was the structure considered rigid or deformable? It was...
Go ahead.
Oh, no, I was just gonna say it was, we had it as, we used elastic isotropic elements, but I think we set the stiffness pretty high just to basically make it rigid, but we can also do deformable structures as well, but the structure wasn't particularly flexible, so
we don't limit types or materials of the structure, so any models you can define OpenSees that can be used.
Okay, and then from Mike Greenfield, let's see, could aspects of the OpenSees PFEM be adapted to analyze lines or landslide runout? For example, could you use the mesh and remesh functions for large deformation analysis with arbitrary ND materials?
I think you could, but the only issue is if the object or the landslide, the rockets or anything, is moving, it depends on if the elements consider large deformation. If it does, it could be easier, but if it doesn't, you need to remove this the structure model or the landslide model and recreate it every time step.
Okay, and then it looks like the next two questions are similar. So from Azine Ghaffari as well as Balint, how long did this 15-second kind of PWRI experiment or analysis of that experiment that you showed in the presentation, how long did that take to run, on wall time? All right.
2 to 3 hours.
2 to 3 hours. Okay. Okay, and that's about how many time steps it was?
It was like 15 over 0.006.
Or 15 or 15 times. Oh yeah. Yeah, a couple thousand, I guess.
Yeah.
give or take an order of magnitude. Okay, and then Belinda, another question on how much gigabyte of data was, or how much data was produced, I guess, meaning the output
Yeah.
with the recorders and output files, like what was
Mhm.
the size of that data?
Yeah, I can check the data I just saved. So that's good here. So I was just run for one step. So for one step, it was like 40 megabytes.
So that's with all like the velocity and pressure
Yeah,
for all the particles.
right,
Yeah. Oh, and then you record that for every time step,
right, right,
so that then you could load all that into ParaView
right.
and then see the whole
Mm-hmm.
response history with all the particle locations. So about 40 megabytes per time step. So yeah, okay. All right, and then from Andre, good to see you, Andre. So following up on Farzine's question on 3D modeling, one, what methods for analyses do you suggest for the PFEM? And then are there specific parallelized analysis methods implemented for PFEM? Let's see.
So what methods for analysis?
Yeah, I guess I'm a
Yeah,
little unclear on the first part, but but maybe could you comment on the parallel computing with PFEM? I know you're kind of working on that. Or what are the big bottlenecks with PFEM analysis, and how does parallel computing help speed things up?
Currently, we do have some parallelism for PFEM, especially when you're creating particles, when you're moving the particles, when you do updating the background mesh. So these particles are done using all your threads in your laptop or your computer. So it's a multi-threads parallelism, but we not yet have the multi-processor parallelism, because the solver part is a problem. It's interact with even you use OpenSees MP, you don't get it. That's something we're working on it.
Yeah, especially for 3D problems, it
Right.
becomes very difficult to do on a single machine. Oops.
Yeah.
Hit the wrong button there. Okay. And then from Vedran, good to see you on here. Regarding a landslide runoff, can the landslide be modeled by varying the density and viscosity of particles?
Yeah. That's actually what the Aniate and Edelson, what they did in classic PFEM when they did the landslide. They did this. They just assign very high viscosity for the particles and treat it as kind of solid.
Okay. All right. It looks like that's it on the questions from the Q&A. And we have a few more minutes. But Balint has one more. Really impressive work. Thank you. Do you think this tool can make it into engineering practice, or is it mostly an academic work? I don't know. Maybe Balint Balint could answer that, but I think right now it's mostly academic. But I mean, we're seeing, it is kind of making its way into practice, maybe not directly, but indirectly, certainly.
We do see interest from the practicing engineers too.
for the PFEM.
Yeah, yeah.
And yeah, OpenSees in general. Yeah.
Mhm.
Yeah. Okay. Let's see. Okay. Well, I guess, if there are any other questions, just you can follow up with Minjie and me directly. But I think at this point, I'll see if Cole, do you want to close us out? And
Yeah.
Yeah.
Thank you so much. This was wonderful. Thank you to the audience for all of your questions. This has been recorded and we will publish it on the PacTrans YouTube channel. And then we'll also circulate it in our newsletter and on our website. If you don't know how to find any of those, you can email me at PacTrans, PACTRANS @uw.edu, and I can make sure you get a copy of the recording. Huge thanks to Michael and Minjie. This was great. And then also keep in touch with PacTrans because we do at least one webinar a month on a variety of different topics. So thank you so much. And with that, we will adjourn for the day.
Thank you.